Tedesco's thesis defense, his PhD thesis. Matt came to us in 2014 from University of California, Davis campus. He has two bachelor's degrees, one in mechanical engineering, one in aerospace engineering. And he got a master's with us a couple of years ago. And he's going to be talking to us today about helicopter power optimization and mechanical vibration minimization. So, Matt, with that, the stage is yours.
Awesome. Well, thank you, Dr. Hall. And to my committee, if you ever have any questions, feel free to let me know, or obviously you can wait till the end to ask. Appreciate everybody coming out, especially on the live stream. I love the support. And without further ado, why don't we talk a little bit about helicopter rotors and power and vibration optimization. So before we jump into a bunch of math, I think it's important that we start by kind of figuring out why we're doing this in the first place. So we have two plots on this chart here. Both are showing on the x-axis advance ratio, which is effectively forward flight speed. And on the left plot, we notice we have normalized induced power, which is just the induced power coefficient divided by the lift coefficient squared on the y-axis. And we have three curves. One is the Glauert limit, which is effectively the absolute lowest that you can get for basically any flying vehicle. And then we have two other curves collected by Hall and Hall, which are for trimmed and untrimmed rotors at these different forward flight speeds. And the big thing that we notice is they're all above the Glauert limit, and there are these interesting spikes that happen at faster speeds, basically telling us power is going to be fairly high, especially higher than the Glauert limit for these rotors. So it's going to be a good idea to be designing for lowest power possible. But on the other side, we still have forward flight speed on the x-axis, but on the y-axis we're looking at vibration amplitude. This is effectively non-dimensionalized, is what we call G-loading. So the higher we go, the more vibration we see. And the more vibration we get, the more airframe fatigue we'll tend to see, which can lower the lifetime of an aircraft. So we notice there's two peaks, one here at descent, and then one over here at a higher thrust value. And what this means is that as we fly faster, as we get into this descent region, we're going to have higher amounts of vibration, which isn't going to help the aircraft. So it's also a good idea to be designing for minimum vibration as well. So this is kind of setting the stage. We want minimum power, we'd like minimum vibration, but how do we do it? Well, to do it, we need to set up an optimization problem. And to do that, we need three things. We're going to need to decide what we're going to optimize with respect to. This is known as the design variables. What value should we be optimizing? That's known as the objective function. And then, should we be considering any constraints on the system? This is known as the constraints. So in order to get these things, we're going to need to consider the following elements. For this rotor, how are we actually going to model the system? This is going to come down to aerodynamics, structural, and possible couplings. Once we design the model for the system, how are we actually going to solve for the forces and the power? And then the motion and vibration. And then finally, with all of that in mind, how are we going to create these objectives and constraints we're talking about? So, I just want to do a quick recap. A lot of this I know you definitely have heard in the master's thesis, but I think it creates a holistic picture. For our aerodynamic model, we're creating what's known as a lifting surface model. I've given you a picture of it here on the bottom. This rotor in this case is flying from right to left, rotating counterclockwise. The rotor is being modeled as a set of ring vortices. We call them gamma A. There are these red squares that we see here. And then the wake, which is basically going to be where this rotor has been in the past, is going to be modeled with these black squares here. One thing to also point out that we discussed previously is that especially here on the retreating side of the blade in the reverse flow region, this is where the flow is actually flowing to the left in this case instead of to the right. We have actually put the panels on the opposite side of the blade in order to effectively model the reverse flow region. Now, one thing that we've actually added since then is what we've called the hybrid wake model. We found that in some previous studies that having equal spaced grids, especially near the airfoil, is super important if you want to get good unsteady lift calculations. However, you can tell these grids are definitely not equally spaced. And so what we decided to do is create, as I've zoomed in here on this section, a grid that's as close to being equally spaced as possible near the airfoil itself. And then it goes back to course after that. So basically, we can pick as many panels as we want, but as we're going to see on this slide, that might not matter as much as you think. What we did to test this is we effectively plotted the Theodorson. For those of you in the audience that may not know what that is, that's basically when an airfoil is oscillating up and down, and we calculate the lift. The theoretical Theodorson is in the solid blue curve here. And then the results without using this hybrid wake model are in blue. The blue circles are equally spaced grids, and they do very well. But the minute you start using grids that are twice or even 4 times as large, you get very poor results. However, if you start using the hybrid wake model with 10 panels or even just 1 panel, when you start using these grids, they get much better in comparison with their counterparts in blue. Especially when we consider that for us, we're basically going to be in this region here, pretty much not much further than that. This is definitely a lot better agreement when we use this hybrid wake model. So now that we've created the aerodynamics model itself, it's going to be important for us to look at the forces and the power that it creates. When we look at the force, we're going to be calculating this using a Kelvin impulse method. So we're creating the Kelvin impulse as being the integration over the wake of the potential. The jump in potential across the wake is equal to the circulation, so we can actually rewrite this to be an integral of the circulation. When we divide by the period and take the negative of this Kelvin impulse and divide by the period, that's actually going to get us the average force for the blade. Now, this is in continuous form. However, it can easily be written in a discrete sense as a matrix B times a vector of those gamma wakes, those black panels that we saw earlier, to get us the average force. Now, when it comes to the moment, we have also discussed this a little bit in the past. We actually need to switch to using a near field approach in order to calculate accurate results. And so in order to do that, we're going to use the unsteady incompressible form of Bernoulli's equation and average it over time. So what this ends up looking like is like this integral right here. We notice that now we're doing an integration over the airfoil, not the wake. We see our traditional steady lift, rho u cross gamma, and then an unsteady lift d gamma dt, both crossed with basically the position vector r to get a moment. This is integrated over the airfoil and then integrated over time to get us all the moment, and then divide by the average, divide by the period to get us our average moment over that given period. Once again, this is in continuous form. We can discretize this and write it as a matrix D times a vector gamma A, which is those red rectangles that we saw earlier that model the airfoil. So when it comes to the power, we're going to be looking at the amount of kinetic energy that we're going to deposit into the wake. So this is basically 1/2 density times induced velocity squared. Now, for us, we can write this induced velocity as the gradient of our potential. And using Green's theorem, we can write this instead of as a volume integral, we can write it as an area integral over the boundaries. And the only boundary that's going to have circulation is going to be the wake itself. And this will give us an integral of this form. Now, because the induced velocity is a function of the circulation, this is quadratic in gamma. But similar to the previous integrals that we've seen, we can take this continuous integral and write it in a discrete sense, where now you notice we have 2 gamma wakes because it's gamma wake squared. We decided to include viscous power by simply looking at the rate of work done by the drag force. And to simplify things a little bit, we've just decided to include the drag coefficient here as being a quadratic drag polar fit to data. We actually took the data from a Hall and Hall paper back in the early 2000s, I think 2010. And then from there, we're going to get an integral of this form. You'll notice we'll have a constant. This is a constant term. This will include another quadratic term and a linear term, which is just going to modify our discretized version with another quadratic term, a linear term, and a constant. So with this in mind, this is our final power. This is what we're going to use as one of our possible objective functions in the future. So that's how we're going to get our forces and power. But when it comes to the constraints that we might have to consider, we're going to have to consider the no penetration boundary condition, basically saying that no air is going to flow through a solid boundary. So what this does is this is going to, as we see in our equations here, it's going to relate our airfoil circulation, and it's going to multiply by a matrix AAA at a given time step. This is going to relate the influence coefficient of an airfoil panel on another airfoil panel. AAW will relate the influence of a wake panel to another airfoil panel. And then AA theta is going to be the relationship of our design variables. Just as a recap from the masters, the design variable we're going to consider are controls of pitch. So as the blade goes around, it's going to do this a certain number of times. This is where this is going to come into our equation. Finally, we do have a second set of equations down below here. This is known as Kelvin's theorem. This is what we use to relate our wake circulation to our airfoil circulation. It basically is going to be a time derivative of the airfoil circulation relating to the wake circulation. So this is at every time step. We can combine these for all time steps and get a matrix equation of this form here. And just as a heads up, if we knew theta, this would actually have enough equations and enough unknowns to be perfectly solvable. But if we don't know theta, we could just use this as a constraint in our optimization. Now for us, this was too many unknowns, and we wanted to reduce this, so we decided to use two methods. The first was static condensation, where basically what we do is we say we're going to solve for gamma A in the top equation. We're going to plug that solution into the bottom equation. And then if you want gamma A at a later time, you can solve for it. When you do that, you'll get an equation like the bottom here. You'll notice this bottom equation doesn't have gamma A in it anymore. This is because you could back solve for it later if you so desire. By doing this, you're severely reducing the number of unknowns that you have. So roughly speaking, for us, we would have started with about 40,000 unknowns. Now we're looking at more like 5,000 unknowns, which is a significant reduction. But we wanted to go further. So the way we did that is by using harmonic balance. With harmonic balance, we're looking at the spectral domain instead of the time domain. So instead of looking at the time values of gamma wake, we're looking at the Fourier coefficients gamma hat. You can think of these as sines and cosines. And this E is our inverse Fourier transform that helps us to get from one domain to the other. In this case, from the spectral back to time. So before harmonic balance, we see an equation like this. And below that, we see that gamma wake has been replaced by E gamma hat. And one other addition has been made. It's this E plus. This is what's known as the Moore-Penrose pseudo-inverse. This makes our matrix square so that it's solvable, and gives us an equation, if we make it more succinct, of this form. So now, with doing this, we've reduced our equations even further. Instead of looking at 5,000, we're looking at less than 100, which is a drastic reduction when you consider that, as we see up here, computations can scale with n cubed. So that's a severe reduction. Okay, so that's the aerodynamic model, kind of a recap of the masters. So from here, we decided to take it to the structural model. So the structural model we decided to be inspired by a paper actually written by Dr. Dow and Dewey Hodges. And you actually see a couple figures from that paper up above. Just for some context, the x-axis here is the axis of rotation of the blade. The blade is rotating counterclockwise here. The z-axis is basically normal to the plane of rotation, and the y-axis is normal to those two axes. The picture on the right here is just a cross-sectional view of the picture on the left, so you can see torsional motion a little bit better. For us, our system is going to undergo three primary types of motion. We're going to go flapping motion, which is this kind of motion here. We're going to undergo lead lag motion, which is this kind of motion in plane. And then finally, torsional motion, which, as you can see from the cross-sectional view here, is going to be the twisting of the blade. More generally for us, because these are all different dynamic values, we're going to wrap this into one vector Q, and this vector Q will usually contain all these different types of motion. Now, one type of motion I do want to point out that we decided to talk about a little bit differently is the axial deformation. Because we know that helicopter rotors are significantly stiffer in the axial direction than, say, the flapping or lead lag direction, we decided to use an inextensibility condition, which takes the following form below. This is basically saying that there isn't any pure axial deformation, and that any axial deformation is going to be due to deformations in other directions. So to derive the equations of motion, we took a Lagrangian approach similar to Hodges and Dow. And basically what that means is we're going to look at the kinetic energy and the potential energy of the system. This is completely outlined in the dissertation, but at the end of the day, you're going to get something that takes this form. When you use Lagrange's equations on this Lagrangian, you'll get three differential equations that look like the following. And we see some players that we're used to seeing. We see our basically mass times accelerations, or our inertias times accelerations. We see our typical kind of beam, Euler-Bernoulli beam theory fourth derivatives. We see some terms such as this one here that is due to Coriolis effects. We notice that there are also some terms, this E here, which is basically an offset between the center of gravity and the axis of rotation. And then finally, we see this P term. The P term is effectively what we call a centrifugal stiffening term. This is because as it bends, it's going to tend to want to be pulled inward, which is actually going to stiffen the beam in that direction. Of course, with any good differential equation, you're going to need boundary conditions. And so for us, at the root, we're using geometric or essential boundary conditions. And because we're going to be dealing mostly with cantilevered beams or fixed end conditions, you'll notice that these are your typical fixed end conditions. At the tip, we're going to be using the natural boundary conditions as follows. You might also recognize these as no shear and no moment at the tip. So instead of solving these differential equations directly, what we decided to do is use a finite element model where we've split up the spatial and temporal dependence. The spatial dependence is going to be based on the shape functions n. And these n's are determined by Hermite interpolation. This is basically saying that each n is going to have a value of 1 in either the 0 or first derivative at each endpoint. And then the temporal dependence is going to be at the different endpoints. So you'll notice here we have the 1s and the 2s. Those are the different endpoints for each of our values of lead lag, flapping, and torsion. When we plug this into the Lagrangian that we saw before, we're going to notice the integral pulls into the ends. This is because the q's are no longer functions of space. And we can do these integrals a priori. And once we do that, we'll get a Lagrangian of this form, which looks very similar to what we saw before. And we can once again use Lagrange's equations and do a little bit of simplification to get a set of, really one equation of this form, where we see we have our q double dot, our q dot, and our q terms. Now, similar to before, we can actually use harmonic balance here, where instead of looking in the time domain for q, we can look at q's harmonics. So we notice we have a second derivative that's now turned into a pseudo-inverse times d squared, which is our typical derivative operator, just so you can kind of see notionally this is where we have j omegas on the diagonal, multiplying by the correct harmonic amount, either 2 omega, 3 omega. And this is a second derivative, so we do it twice. First derivative, do it once. No derivatives, do it no times. And so we can now actually simplify the equation even further. So instead of having q double dot, and q, it can now be one matrix just times q. We also still have theta, and we also still have b. But at the end of the day, this set of equations is our final set of equations of motion for our structural model. So similar to before, where we created power for the aerodynamic model, we need to create an objective function for the structural model. And here, the key is going to be focusing on the average of the square of the vibrational loading at the hub of the rotor. Looking at an integral, it's going to look something like this, where we have our vibrational forces at the hub, minus the constant, because the constant is always there. It's not really a vibration. And there's a lot of different ways we can model this, but we decided to start simple, and we can always take it further later on. And the way we simplified was doing three things. The first was saying that transmitted forces will all obey Hooke's law, so the force is going to be proportional to some kind of spring times a displacement. We're going to say the hub mass is considered infinite, or you can think of it as the rotor's been attached to the Earth, so transmissibility isn't a question here. And then finally, we're only going to consider flapping motion to start this analysis. So the force of the hub is going to basically be a spring constant times our flapping at the hub as a function of time. So with this, what we can do is write out this flapping motion at the hub as a function of time with the harmonics, similar to how we turned q into q hat. And after moving stuff around a little bit, you'll get that vibrational integral will take this form. The big thing to point out here is this sigma sum. This is because every blade is contributing to the vibrational forces at the hub at every time. It's not one blade, it's B blades. And so you have a harmonic for every single one of those blades contributing. Lucky for us, this doesn't change the fact that sines and cosines are orthogonal to each other. And so what this ends up simplifying to is summing up the harmonics they're integer multiples of the number of blades. So as an example, with a 4-bladed rotor, you'd sum up 4, 8, 12, 16, so on. You do also multiply by b squared. That does come out of the math as well. So all of this can be written, as you can see, it's a quadratic again. So this can also be written in a quadratic form similar to our power, where we have this matrix V in the middle. And this matrix V is basically just going to isolate the correct W's and multiply by the appropriate constant bk squared over 2. And all of this will give us another objective function we can use in our analysis. So before we move on to the coupling, I think it's important that we validate this at least a little bit. And the way I decided to focus on in this talk, we did a couple more cases in the dissertation, is focusing in on what's known as the Heart-2 rotor. So the Heart-2 rotor is a test rotor that was created at DLR in Germany. It was used by a lot of different organizations, including, I believe, NASA for a little while. And it's basically a Mach-scaled BO105 like we saw on the title slide earlier. They collected a lot of different data for this rotor, and so it's a great way to start comparing to known experimental results. Just for some data, so you can see at least a little bit about what this rotor looks like, this is just some basic information about the rotor, and this is some basic information about the constant chord cross-sectional properties for the rotor. And so a great way to compare this is by looking at what's known as the fan diagram or the Campbell diagram. Basically what this is on the x-axis, we're looking at the rotational velocity of the rotor, non-dimensionalized by omega ref. And on the y-axis, we're seeing the eigenvalues, or the natural frequencies, of each of the first 6 modes for this rotor. On this plot, we're seeing 2 different sets of curves. One, the solid line, is the finite element code used at DLR to calculate these modal eigenvalues, or natural frequencies. And the dotted is natural frequency analysis done with our structural equations of motion, as we saw in the previous slides. So first off, you're seeing some significantly good agreement between the dotted lines and the solid lines. Also, some interesting things. You are seeing some significant veering, especially for the first flapping and first lead lag, around an over omega ref of 0.7. Just for context, for those of you that are interested, for most of our operating rotational velocities, we will be operating at 1 for most of the time. Okay, so we've created the aerodynamics, we've created the structural, but now we need to put the two together. So in the aerodynamics model, we've basically focused on the lift generated on the airfoil due to circulatory and non-circulatory effects. But alone, it assumes that the thing generating that lift is rigid, and it undergoes a prescribed motion. For the structural model, it does model the structural motion, given the rotation and the boundary conditions. But alone, the structure isn't affected by external forces like lift. So, for the aero model, we need to include the motion of the system from the structural model. And for the structural model, we need to include the applied forces from the aero model. So how do we do that? First, let's focus in on how we're going to include the motion in the aerodynamics model. So for us, there's 3 primary motions that we're going to need to consider. The first, in the top left here, is that as we have a torsional angle, this is going to cause the free stream velocity to possibly have a little bit more of that normal velocity on the airfoil. So we'll need to account for that. On the right side here, we have our flapping velocity. The flapping velocity will also create a normal velocity on the airfoil that we'll need to include. And on the bottom, we have a torsional velocity, so an angular velocity, which does create a tangential velocity depending on how far away each panel is from the axis of rotation. So all 3 of these values have to be accounted for as we create the motion in the aerodynamics. So at the end of the day, we're basically going to do this after doing a little bit of math by including 2 new matrices. AAQ, which is going to multiply Q, so it can include this effect in the top left, and AAQ dot multiplying Q dot, which will account for the top right and the bottom. Bless you. So once again, we can use our friend harmonic balance. Harmonic balance allows us to write this instead of being 2 different matrices using a derivative operator again, so we can write this as 1 matrix times Q, or in this case, just so we can see it, Q hat. Now, when it comes to including the applied loads in the structure, we're going to use a principle known as virtual work. Virtual work is basically where we take virtual displacements multiplied by the forces. And we're going to have to integrate this over the airfoil because that's where the forces are occurring. Luckily for us, similar to how we created the unsteady incompressible form of Bernoulli's equation for the moments, we can use that for the lift as well. So the force is basically rho u gamma, our steady lift again, and d gamma dt, our unsteady lift again. All of this can be discretized as the following, where b1i is basically going to be every single vector here that we're seeing crossed with the free stream velocity at the given panel. And b2i is basically going to be the direction of the normal vector multiplied by the panel area. Yet again, we can use our friend the harmonic balance method to write gamma a dot as being a derivative operator times gamma a. And so we can write all of this as one matrix times the circulation on the airfoil. Once we get to this point, it's possible to do a little bit of math, which once again is outlined in the dissertation, to rotate this into the right reference frame, use our finite element methods again, and then include this in our model through a matrix that we'll call AQA. That will effectively model the applied loads in the structure as a function of the airfoil circulation. So similar to before, it's important to kind of validate if this is actually working. So we go back to the Heart 2 rotor for a moment. And instead of looking at the Campbell diagram, we're going to look a little bit at the tip displacements of the Heart 2 rotor. So for some context, these cases were run at an advanced ratio of 0.15 with an angle for the shaft of 5 degrees aft. So that means it's actually tilted backwards. This is usually to model descending flight. What we're looking at is on the x-axis, we're looking at the azimuthal angle, which effectively is time. And on the y-axis, we're looking at the percentage of each motion compared to the radius. That's why we have 100 W over R and 100 V over R. For each set, we have some different sets of curves. If we take a look at the blue circles like we see here, we're looking at the experimental results from van der Waal. This is the test documentation for the Heart 2 rotor. Our results, which we can see here in blue, are basically computed using our structurally coupled model now. And then we also have two different sets of comparisons for each plot, usually collected using either CAMRAD or DIMOR from different authors, particularly Park, which we see here in the yellow and the orange. And sometimes we've used results from Jung and Lim depending on availability of results. So key takeaways here. There is actually very good agreement, especially when we compare with the other methods used by Park, especially in flapping. The general trends are there. The magnitude is roughly there. And especially if we look at torsion, I would say that we're doing much better than DIMOR actually did compared with the van der Waal experimental results. The interesting thing is in lead lag, we are at a little bit less of a magnitude compared with Jung and Lim. But this bigger difference that we're seeing here between the experimental and the CAMRAD analyses has actually been well documented in the literature and could possibly be an experimental error. And then finally, if we take a look at the controls, there's very good agreement. At worst, we're looking at about half a degree of difference in the values, which is to say that this is very good agreement considering the size of the model and what we're comparing to, which is experimental results. All right, so we've created the coupling, structural, we've created the arrow. We come back to what we were talking about before. We need design variables, we need an objective, and we need constraints. For our design variables, we've created two variants of circulation, pitch controls, as we talked about as the blade twists, and with dynamics, motion of the rotor, which we're calling Q. These can possibly have reductions, such as static condensation or Guyon reduction for some others, and harmonic balance, where instead of looking in the time domain, we're looking in the spectral domain. When it comes to objectives, we've found two, it seems. The first is looking at the power, or what we'll colloquially call P-opt. This is our quadratic, linear, constant term, without harmonic balance and with harmonic balance. This is just so we can see what that would look like with harmonic balance. And then finally, we also have our vibrational loading minimization, which we'll colloquially call G-opt for G loading. And here is our quadratic term that we derived for our vibration. These are our two objectives that we'll consider. And for constraints, we've got some as well. I put them in a matrix just so we can see them all loaded up together. We've got our no penetration boundary condition paired with Kelvin's theorem. We possibly could include our structural equations of motion. And we didn't talk too much about this, the trim constraints. The trim constraints are effectively saying, force this lift to happen or force this moment to happen. Usually we'll use this to say a certain lift has to occur and that there is no roll or pitch moment. Also to point out, we notice that we have our AQA and our AAQ. Those are our coupling terms that we just finished deriving. Now, lucky for us, the objectives are quadratic. The constraints are linear. This is a quadratic programming problem and can be solved with a matrix solve. So just so we can see what some of those look like, we have a couple here for you. The first is the rubber rotor solution. We call it this because if you notice, the only constraint that it considers is trim. And it optimizes for power. So no consideration is put into what the rotor feasibly should look like. This should create the absolute lowest amount of power we would see for this given rotor. Below that, though, we have the realizable rotor. This is what was studied significantly in the master's thesis, where we've added a new constraint. Here is our static condensed Kelvin's theorem and no penetration boundary condition. But we're still optimizing for power. And then finally, we have what we're going to be looking at a fair amount today, which is the aeroelastic coupling for p-opt and for g-opt. We'll notice really the only big difference here is we have our objective here for p-opt and our objective here for g-opt because this one's hitting Q, the other one's hitting gamma. So these are the matrices that we're going to be solving moving forward here. So now it's time to take a look at some results. So for us, we're going to be studying some conventional rotors here. For structural properties, we'll keep the structural properties of the Heart 2 rotor, including things like the built-in twist of the rotor. We'll put in a 3.75% root cutout. For the details of it, this is basically to the blade bolt of the rotor. We're going to put in a shaft angle of 5 degrees forward. This is to simulate forward flight instead of descending flight. And we'll be studying a couple different things. The first is advance ratios, or forward flight speeds. And the second is various sets of controls. So this is, if we're studying 1 per rev control, it can twist up and down 1 full twist, 1 time every revolution. If it was 2 per rev, 2 times, 3 per rev, 3 times. A couple interesting things to point out here. First is the number of harmonics that we're going to use. This is actually a little bit higher than we did in the master's thesis at 13. Primary reason for this is so we can actually see more than just 1 harmonic of vibration, because if you remember, we're only going to see for a 4-bladed rotor 4, 8, 12, 16. And then the other thing is all of this has implicitly implied the lightly loaded assumption. Basically what this means is that the wake is okay to be rigid and prescribed. And that means that we can't fly below a certain advance ratio. And for us, that's about an advance ratio of 0.07. So we're not going to see results close to that. So one of the first things that's important to study here is just a couple different advance ratios before we get into huge sweeps. And so I've picked 2, a mu of 0.45, which we see here, and another one mu 0.3. Mu 0.45 is really on the fast side of the envelope, and then mu 0.3 is moderately fast to moderate speed. And what we're seeing on this plot here of this table is the mu 0.45 4 per rev control. We're seeing the controls as we descend here. So we have our conventional, our cyclic for sine and cosine, our higher harmonic control 2, 3, and 4, sine and cosine. We see also for convenience the power normalized by the lift squared and the G loading for each of these cases. So each case on the first column is the power optimization without including dynamics. Second column is the power optimization when we do include dynamics. And third is the vibration optimization when we include dynamics. So some key things that we're starting to see here. First, going from no dynamics to dynamics, we do not see significant changes. In particular, we see this in the cyclic for sine. There's not a significant difference going from 8.9 to 8.5. There are little differences in the higher harmonic controls, but when you consider that the largest values, such as the 10 and the roughly 9 degrees here, aren't changing much, there isn't significant changes going on in our controls. And this is mirrored in the power. We're not seeing significant changes in the power either. However, the minute that we start optimizing for vibration instead of power, we're able to get the G loads down to 0. Now, this makes a little bit of sense because we have just enough unknowns to perfectly optimize the system for vibration to get down to exactly 0. Because remember, we're only keeping 4, 8, and 12 harmonics. But this comes at a cost. The power nearly doubles. So the power nearly doubling is causing a significant twist in my side, because that's not something that I would be willing to put up with. And on top of that, we notice that there are significant changes occurring in the controls, particularly in the higher harmonic controls. Interestingly, though, we actually don't see significant changes in the collective or cyclic controls. So big takeaways here: higher harmonic controls are jumping in a lot. Power is doubling, but we are able to get the vibration all the way down to 0. So we're going to have to come back to that a little bit later. But for now, let's keep going and talk a little bit about the actual dynamics of the system, what's happening. So these plots should look a little familiar from a little bit earlier in the talk. We have our azimuthal angles again. And on each of these axes, we're looking at the percentage of flapping motion. I've decided to focus just for now on flapping, since a lot of these trends are going to occur in every set of plots. And what we've done is we have included all the different sets of controls for the mu.3 on the left, the slower speed, and the mu.45 on the right, the faster speed. The big thing that we notice is once you get to about 2 per rev to 3 per rev control, once you start moving to 3 and 4 per rev control, there aren't significant changes in the dynamics, which is seeming to suggest that at that point you've optimized the system about as much as you can for power, which is actually in agreement with what we've found previously in the master's thesis and what Giovanetti and Hall have found in the past as well. This is a little bit different over here on the 0.45, simply because we're flying faster, so higher harmonic control is going to make a little bit more of a difference. So there are slightly bigger differences than we would see over here in the mu of 0.3 case. But keep in mind, this is only for power optimization. So the natural question would become, what happens if we start to include vibration optimization? So that's what we have here. I've decided just for highlighting this, we're only going to focus on the mu of 0.3 case, and we're going to look at each set of controls. So these are the same plots, except now on each plot, we have the trim case for comparison. We have the power optimization in blue and the vibration optimization in orange. For the 2 per rev in the top, the 3 per rev on the right, and the 4 per rev on the bottom. And the big thing that you notice is the more control per rev control that you use, the bigger the difference becomes between power optimization and vibration optimization. When we look at the 2 per rev control, there are slight differences between the power optimization and vibration optimization, definitely. But as you go to 3 and then 4, the shape almost flips completely compared with the power optimization. So there are significant differences in the dynamics of the system as you switch from power optimization to vibration optimization. So the natural next question becomes, well, what's happening to the lift? So if we look at the lift, this is for the lift coefficient evolution of a 0.3 advance ratio, 4 different ways. The top left is the rubber rotor. This is the absolute minimum you can get. Top right, power optimization without dynamics. Bottom left, power optimization with dynamics. Bottom right, vibration optimization with dynamics. We notice that going with no dynamics to dynamics, there are not significant changes. This is all kind of in alignment with what we saw at the very beginning. But the minute that you switch to vibration optimization with dynamics, we see huge changes. Instead of having this bubble here of a high lift coefficient at an azimuthal angle of about 90 degrees, we notice that instead we're seeing 3 significantly large groupings of high lift coefficients, roughly fore and aft, and in the reverse flow region, mostly to maintain trim. Also interesting is if you notice, this is a heavy 3 per rev, and if you remember back from our table, there was a significant 3 per rev increase in controls. So this is in alignment with what we saw in the control evolution when we did vibration optimization. Okay, so that was looking at 2 advance ratios. So what happens when we start to sweep through advance ratios? So that's what we're going to look at next. So on the x-axis here, we have our advance ratios, our forward flight velocities. On our y-axis, we have our normalized induced powers, once again normalized by lift coefficient squared, for a lot of different cases. We see all the per rev control again, The solid lines are not including dynamics, and the dotted lines are including dynamics. I've decided, for the sake of clarity of the plot, not to include the vibration optimization with dynamics because we know from previous plots it's going to be significantly higher, simply from what we've seen before. The key takeaways that we notice here, though, are that especially here in the realistic region of flight from, say, 0.2 to 0.45, there are not significant differences between these plots. And even if I zoomed in, we would not see significant differences between the dotted lines and the solid lines. Once again, showing us that in that realistic flight regime, there's not a big difference if we include dynamics. Where we do start to see some differences is when we get into this 0.6, 0.7 regime, really fast flight, as Ormiston might call it, the critical advance ratio. And we notice that for the 2 per rev control, there's actually a large difference between the with and without dynamics. But for the 3 and 4, there really isn't. Part of the reason for this is that the 1 per rev control near this advance ratio can't maintain trim. That's actually what Ormiston found. And so the 2 per rev control is basically being forced to maintain trim and can't focus on other things like reducing the power that might be added by the vibration. We're actually going to see that a little bit on this next plot, which is looking at, once again, the forward flight velocities. But now we're looking at the G loading. This is the vibration of the rotor's hub. And we're seeing this for 2, 3, and 4 per rev control, power optimization, and vibration optimization. Looking first at the solid lines only, we notice that there is a significant difference between the orange curve here at 0.6, 0.7 versus the yellow and the purple curves. This is going in alignment with what I just said earlier, which is that for the 2 per rev control, it's so focused on maintaining trim that it can't reduce the power that might be added by this vibration, whereas the 3 and 4 per rev can reduce it at least a little bit to get that power down more towards its base level without dynamics. Now, when we start to look at the dotted lines, though, we notice that the 2 per rev control, when you optimize for vibration, once again, it really can't do much. It's basically tracking the orange curve as before. But the yellow and purple curves are significantly lower than their solid counterparts. In fact, the purple curve is actually hard to see because it's exactly 0 for everything. Once again, this is because we have just enough unknowns to create exactly 0 for the system. In reality, this would actually be just a very, very low curve. So what this is telling us is that more controls, better vibration control, but at the cost of power once again. So it begs the question. We saw before, you can reduce the vibration to 0, but it comes at a huge cost. We can't pay that cost. So what do? Well, this is where we need to consider both power and vibrational loading. So the way we do that is with a multi-objective analysis. So you'll notice that we have our 2 objectives again, but they're multiplying alpha. This alpha you can think of as like a percentage parameter, where when we make it 0, we're doing a pure power optimization. And when we make it 1, we're doing a pure vibration optimization. When we do this, one of the first plots we can create is what's known as the Pareto frontier. So the Pareto frontier is, on the x-axis here, our G-load values, and our y values here are our normalized induced powers. Each of these curves was created by iterating alpha. And at every alpha, you'll get a different value for your optimization, and you'll plot that point for each curve. We see 2 sets. The top here is our fast speed, 0.45. Bottom set is our mu, 0.3. We have different sets of controls, 2, 3, and 4 for each. And so that we can see it, we also see a black dot, which represents the trim case for each of them. So the big thing that we notice is that as you use more controls, you're getting closer to the origin. Makes sense. More design variables, you're getting closer to 0. But for each of these curves, there's a significant knee where it becomes extremely costly to pay to reduce the vibration more and you have to pay with power. So for instance, here we have to pay a huge amount of power to reduce just that little bit amount of vibration. But before that, we're actually able to reduce the vibration without paying as much in power. So for example, roughly speaking, moving from here to here, you can get a reduction of about 60% in vibration, and you're only going to increase your power by about 10%. Now, I know that realistically that's still a fairly large value, but when you realize that originally we were talking about doubling the power, that's a lot lower and might be more manageable depending on what your situation is asking for. So the final question that I would ask is, well, why is this happening? What's going on behind the scenes? So to do that, what we're going to look at is two things. On the left, vibrational loading, and on the right, control evolution. Both of these are plotted on the x-axis as alpha varies. Just as a reminder, when alpha is 0, it's p-opt. When alpha is 1, it's g-opt. On the left here, it's the g loading that's on the y-axis, but I've broken it down by the harmonics. So we'll notice we have our total in black, but we have a fourth harmonic contribution, an eighth, and a 12th. The big thing that we notice is that the first harmonic that it tries to tackle is the fourth harmonic. It makes a little bit of sense. In the dissertation we talk about that like harmonics can be controlled by like per rev controls. So the fourth harmonic is the first to be tackled. Then the eighth is tackled, but the one that always sticks around until the very end is the 12th harmonic, suggesting that it's very costly to remove that higher harmonic. Now, how does it do this control? Well, we can look over here to the control evolution. On the top, we have our collective and cyclic controls. And we notice the collective and the cyclic don't change significantly. What does change significantly is our higher harmonic control. We notice that for the 2 per rev and the 3 per rev controls, they almost linearly increase. And the interesting thing is that the 4 per rev actually isn't really touched until the very end, suggesting it's very costly to use 4 per rev control in terms of power, and it won't use it until it's absolutely necessary. We notice it here, and it spikes right at 1. Finally, we can kind of see what this is looking like from a lift perspective. So I've given here is the lift coefficients for the 0.45 case. We're using 4 per rev control, 6 different ways. We have our p-opt up here, which we've seen before, our g-opt, and then in between different alphas. And the big thing that you notice is once we hit an alpha of 0.6, and even in some ways 0.1, the shape of the lift is not changing significantly until we hit exactly 1. Once we hit 1, we see drastic changes in this region up here, becoming more smeared towards an towards an azimuthal angle of 90 degrees. We notice that this region here tends to get a little bit more negative and moves closer to about 45 degrees. This is suggesting to us that in that alpha region, we're noticing not significant changes in the lift distribution, but we're still able to reduce the vibration. Okay, so with all this being said, what have we done? Well, we've taken what we've already created. We've added a hybrid wake to better model the unsteady lift. We've included static condensation and harmonic balance to reduce the computational complexity. We've derived a finite element model inspired by Hodges and Dow to allow for motion of the blade. We've created an aeroelastic coupling with that structural model to create a comprehensive model of the system. And finally, taken all of it and optimized it for vibration and for power. From all of this, what have you learned? Well, from what we've learned in previous regions, the use of higher harmonic control reduces power about 1 to 4% in that 0.2 to 0.4 advance ratio. And this is something that we've seen from the master's thesis. But now we've also noticed that use of dynamics in power optimization cases resulted in, at best, 1% differences in that 0.2 to 0.4 realistic flight regime, suggesting that it's not adding a significant amount of data to that power optimization. But as you fly faster, higher harmonic control becomes necessary to reduce the power effectively. When we look at vibration reduction, we can do it pretty significantly using our higher harmonic control, but it comes at the cost of huge power increases if we're not careful. If instead we consider a multi-objective analysis where we look at power and vibration at the same time, we're able to actually see a 60% decrease in vibrational loading for 10% increases in power instead. So with that in mind, I want to just thank my advisor, Dr. Hall, for all the amount of work that he's done with me through all of this, and just quickly shout out to NDSEG for all the help they did for me to get to this point, as well as the Army Research Office at the beginning of my career. And with that, I think... okay, so I do have one question, it seems. So somebody actually asked the question, do you solve the structural and aerodynamic equations simultaneously? Yes. So you can pick if you want to do the aerodynamic equations only, you can. But if you want to do the structural equations, those are coupled and can be solved with the aerodynamic equations as well. And I don't see any other questions. So thank you, everybody, for attending. I'm going to end the live stream now, but I appreciate it, and I'll let you know how it goes.